Hello, everyone. Uh, my paper presentation for today is Budget Deadline Constrained Workflow Planning for Admission Control. In the last paper, I have already spoken about how to map a workflow on a particular resource. Now, I'm going to speak about how to map a workflow on a particular resource with two constraints, that is, budget as well as deadline. An environment consists of multiple heterogeneous resources. We know that there are a lot of resources of various types in this environment which provide some services that are of different capabilities and are of different costs. Users want to make use of these services to execute a workflow application with a certain deadline and budget. The problem considered in this paper is to find a feasible plan for the execution of the workflow with the specific constraints set by the user. If users agree to admit the workflow, providers can allocate services for its execution in a way that both deadline and the budget constraints are met. If a user may also require a workflow application to complete within a certain budget and deadline. Such requirements are generally recognized as quality of service (QoS) requirements. Now, what is an SLA? SLA is a service level agreement which can be regarded as a bilateral contract between a user and a service provider. In terms of SLA are fulfilled, the user is expected to pay some fee to the provider. Conversely, if the terms of SLA are not fulfilled, the provider has to pay some penalty to the user. Thus, to establish an SLA, the service provider must have a way of determining in advance if it's feasible to fulfill a user's request. In short, uh, the service provider must have a plan if he can satisfy the user's request, and such a plan is called as the BDC plan. If Now we'll see what is a BDC plan: budget deadline constraint plan. Identifying feasible reservation slots on the resources for every task of the workflow in order to provide an assurance that both the deadline and the budget constraints requested by the user can be met is called as the budget deadline constraint plan. And the planning procedure for the same plan is called as the BDC planning. If a BDC plan is found by the service provider, a user's request can be accepted and a relevant SLA can be agreed. Now, for the agreement of this SLA, we have to make a BDC plan. And if the BDC plan is found for the particular request, the SLA can be agreed. Otherwise, a user's request should be rejected. BDC planning should be performed in a very short time because users may require a real time response, and the runtime information on which a planning decision has been made varies over time, and thus a planning decision made using out of date information may not be valid. Obviously, if the information varies per second, like you have some requirements today and you have some other requirements the next day that are not going to be valid. It's outdated information is not going to be valid, so BDC planning should be performed in a very short time. Now we'll see what is BHEFT, a new BDC planning heuristic that is nothing but an algorithm which provides effective BDC planning and fast planning time. As we saw, we have to make the BDC plan very quickly. So you have to have a BDC planning heuristic which is effective BDC planning as well as fast planning time. The proposed heuristic is based on heterogeneous earliest finish time (HEFT) algorithm. HEFT algorithm is nothing but a list scheduling algorithm which aims at optimizing the mix span. That is, it aims at minimizing the overall workflow mix span, minimizing the execution time of the workflow. The HEFT algorithm does not consider the monetary cost and the budget constraint when making the scheduling decisions. HEFT does not consider the monetary cost and the budget. So, in this paper, the HEFT algorithm is extended in order to resolve the BDC planning problem, and the new algorithm is called as the budget constraint heterogeneous earliest finish time (BHEFT) algorithm. Now, let's see what is the problem description of BHEFT. BDC planning problem is to map every workflow task into a suitable service instance and specify an appropriate start time for each task so the overall cost and the time of the workflow are within B and D respectively, where B is the budget and D is the deadline. Notations and assumptions. A directed acyclic graph, that is DAG, is used to represent a submitted workflow application that consists of a set of nodes V, which denotes the task, and a set of edges, which denotes the dependencies between the two tasks. A set of resources, obviously, because we have to map these tasks on the resources. Thus, when a task Ti runs on a resource Rj, it means that Ti uses all the services provided by the resource Rj. What is ETIJ? ETIJ is the estimated execution time for the task Ti on the resource Rj. Pj is the price of that resource. Cost Ij is the cost of running Ti on a resource Rj and is calculated by ETIJ into Pj. For every resource, confirmed reservations may exist. Like for a particular resource, there are maybe already some reservations that exist. This is regarded as existing load on that resource, and it is denoted by L. Suppose L is a resource, ST0, FT0, STK, FTK, where ST is the start time of the reservation and FT is the end time of that reservation. Now suppose there is a resource called L1. The start time of this reservation is from 0 and it ends at 6. Then it is free in the between from 6 to 8. Then again it's going to be reserved from 8 to 12 and so on. This is how the load on the resource is being depicted. Time slot query. Now what is time slot query? The planner has to communicate with the resource owner in order to produce a plan without any reservation conflicts. We have to map the tasks on this resource, but it has to know that when this resource is going to be busy, when this resource is free. So the planner has to send a time slot query to that resource owner, and the resource owner responds with the earliest availability of the resource. Now let LP with the existing load, that is what we saw, on that resource. We define TSQ in the form of FQ, TI, RP, DAT IP and duration, where DAT IP is the time required for all the data to come is available for the task Ti on resource RP, and duration denotes the estimated execution time ETIP. Sorry. Now let's take an example. Let L1 be a resource. It's going to be busy from 0 to 6. There is already a reservation, 8 to 12 and 30 to 50. For a task that is equal to 0, for a task 0 and a resource 1, the execution time for that task is 3 units. Then the TSQ, that is the time slot query, is defined as task 0 on resource 1, dat 01 is 0 and the execution time of that task is 3. Now if you see carefully, this resource is reserved from 0 to 6, but from 6 to 8 it is free. But as this task takes 3 units for its execution, you can't place this task in between these two reservations. So from 8 to 12 it's again going to be busy. From 12 to 30 this task is free. So we allot this task on this resource. We map this task on this resource from 12 to 15. This is how the mapping of the task is done on the reservation, on the resource. The planning model. The planning model consists of 3 main pillars, that is the user, planner and the local resource manager. A user submits a workflow request with budget and deadline to the planner. Upon receiving the workflow and associated constraints, the planner begins planning in order to find the possible allocations for all tasks of the workflow. To do this, the planner needs to find the earliest finish time of a task on a particular resource. To get this information, the planner needs to send an TSQ, that is an inquiry, to the LRM which controls the resource. Once planning completes, the planner checks whether the constraints can be satisfied and responds to the user. If any of the constraints is not met, the workflow request will be rejected. Otherwise, the workflow tasks will be reserved according to the planning result and the user will be notified with acceptance. So this is how the planning model works. Now let's see what is BHEFT. The proposed heuristic BHEFT is an extension of the well-known the list scheduling heuristic, that is HEFT. It is very similar to HEFT. It also has 2 major phases, task prioritizing and service selection. Task prioritizing phase, the priorities of all tasks are computed using upward ranking. If you see, these are the tasks from 0 to 9. So there are 10 tasks, and we have to prioritize these tasks so that we can map it on the resource, like which task has to be mapped first. So for that we have to prioritize the task. How does this prioritizing takes place? We have to rank those tasks, and the rank of task is defined as, suppose you have to calculate the rank of task 0. The rank of task 0 is nothing but the execution time of this task, that is that's the execution time of this task plus the rank of its successors, and we have to choose the maximum of it. Like for calculating the rank of 0, you have to calculate the execution time of 0 to 1, that is 16, plus the rank of 1, execution time of 0 to 2, that is 36, plus the rank of 2, and similarly so on. And you have to choose the maximum of it. Whichever whatever is the maximum is the rank of this task. Now suppose a task doesn't have any successors, like 9 doesn't have any successors, so execution time of this task 9 is the rank of the task. If in the case of childless nodes, the rank equals to the average execution time. So whatever is the average execution time, that is the rank of the task. This is how the task prioritizing has been done. After the tasks are being prioritized, the service needs to be selected on which it has to be mapped. For the service selection phase, the tasks are selected in the order of priority. Each task is allocated to its best possible service. For this, we need to calculate three things: spare application budget, current task budget, as well as the adjustment factor. Suppose we are calculating the kth task is been allocated. We are calculating SAB and CTB of the kth task. SAB is nothing but budget minus CI minus CJ. CI is the reservation cost of the allocated tasks, and CJ is the reservation cost of the unallocated task. Once the SAB is calculated, we have to calculate the adjustment factor. The adjustment factor is 0 if SAB is less than 0, but the adjustment factor, if SAB is greater than 0, the adjustment factor can be calculated. It is nothing but CK bar upon CI bar, that is the ratio between the average cost of the current task of the kth task to the sum of average cost of the remaining task. Remaining, like except the kth, all the remaining tasks. Once the AF is calculated, we can calculate the CTB. Now, based on the allocated budget, a set of services is being made for a particular task, and the best of the service is then allocated to that task. Now, the selection rules for selecting the best service out of the list of services is as follows. If the list of services is not equal to 5, the affordable service with the earliest finish time is selected. If the list is equal to 5 and SAB is greater than equal to 0, the service with the earliest finish time is selected. If the list is equal to 5 and SAB is less than 0, that is, there is no spare application budget, the cheapest service is selected. Whichever is the cheapest service is selected for the task. Let's take an example. If you see here, figure A, example workflow with 10 tasks is used. These are 10 tasks from 0 to 9. This is a DAG example. These are all the tasks. These are the dependencies between the tasks, and these are the nodes. If you see figure B, estimated execution time on task on resources, like how much execution time a task takes on particular resource. Like task 0 takes 26 units of time on R0 resource, 12 units on R1, and 45 on R2. Figure C is the time to transit a data unit between the resources. How much time is required to transit a data unit between resource R0 and R1 is 0.52. This is the price for running a task on different resources. Like to run a task on R0, it takes 0.92 price. It's the price of the resource. So if you see, task 8 needs to transmit 35 units of data to task 9. It needs to transmit 35 units of data. Suppose this task 8 is running on resource 0, and the task 9 is running on resource 2. Then how to calculate the communication cost? It is nothing but 35 into R0 to R2, that is 1.40. Time to transit a data unit is 1.40. So 1.40 into 35 is the delay. But if you see, if 8 and 9 are executing on the same resource, I mean, if they are not executing on different resources on the same resource, the communication cost is going to be 0, obviously. Now, this figure E is the existing load on different resources. Like R0, this is a resource which is going to be, is reserved from 60 to 96.6. Then it's free. Then it's again busy from 177.50 to 196.48. And we have to map all these 0 to 9 tasks in between these resources for its execution. After applying the BDC planning, after you apply the BDC using BHEFT, this is what we get. All the tasks are being prioritized according to your rank in the descending order. Highest rank is being given the first priority. So the tasks are being prioritized. Then SAB, CTB and AF is being calculated. Wherever the SAB is less than 0, AF is going to be 0. Once the AF is calculated, CTB can be calculated. After calculating these three assessment factors, the list of services is being made. If you see for task 0, service 1 is available. For task 1, service 1 as well as 2 is available. So this is all the list of the services, and by the selection rules to how to select a particular service, one service is selected. So if you see for task 0, service 1 is selected. For task 1, service 2 is selected. For task 4, service 2 is selected. For task 2, service 1 is selected. This is how it's been selected. And now if you see, this is the mapping that is already being done. On resource R1, the task 0 is being allocated. On R2, 1 is allocated. For task 4, resource 1 is allocated, and this is how it's been allocated. Now, ways for a scheduling heuristic to produce a plan that avoids reservation conflicts. One way is to produce an initial plan without considering the existing reservations, and then using the TSQ to reallocate the time slot for each map task in order that tasks are initially scheduled. This approach is going to be obviously less costly. The second way is to modify the algorithms to take into account the existing reservations, but this requires more fine-grained changes to the algorithms. Now, what is PSR? To analyze the performance of each heuristic, that is BHEFT, HEFT, the experiment was repeated multiple times and the metric planning success rate, PSR, was calculated. This is how it was calculated: 100 into number of times for which the BDC plan was found upon the number of total repeated times of the experiment. For all the algorithms, this was calculated. Summary of the observations: BHEFT, which takes the existing load of resources into account, is able to achieve a significant improvement on the success rate of finding a BDC plan. That means it had the most planning success rate, as it was very high for the BHEFT, which simultaneously satisfies deadline as well as the budget constraint. Some guided local search heuristic, that is LOSS, may perform slightly better than BHEFT, but at a very higher execution time as well as cost. Thus, they are naturally non-scalable as the size of the DAG increases. With low running costs, BHEFT seems to be a good choice, satisfying the requirements of the BDC planning. BHEFT can effectively and efficiently find a BDC plan under various circumstances of constraint, from tight to more relaxed. Thus, the use of BHEFT can enable a quick admission control decision and make it possible to automate the creation of the SLA, that is a service level agreement. Thank you so much.